We can start now. I think you can see the screen. I have already shared the screen. So can you hear me? Can you see the screen? Hello.
Yes, sir. Yes, sir.
Okay, thank you. So far we have done the following things: that non-deterministic finite automata, the formal definition, example, construction of the automata that recognize certain patterns, and also we introduce NFA, non-deterministic finite automata, and with examples also we have done epsilon moves and epsilon closures, and also we discuss about regular language over alphabets. And regular language is basically a set of string over a alphabet such that those strings are recognized by the finite automata, by a finite automata. That means given a set of string, if there exists a finite automata that recognize it, that means every elements of it are accepted by the automata, then we call that language is regular language. And we also studied about their properties. In fact, we have proved that union of two regular languages is regular by construction of the DFA that recognize their union. So today also we'll prove this particular property using non-deterministic finite automata. In fact, I think I have given some idea about the equivalence of DFA and NFA. So today we start from here. So equivalence means basically if you have a DFA, say M, and an NFA N, so language recognized by the DFA is denoted by LM. It is the set of all string that is accepted by the automata. And similarly, LN is the set of all string that is recognized by the non-deterministic finite automata N. And their equivalence means actually for given N, we can find a DFA. Given an NFA, we can find a DFA such that DFA also recognize the same language which is recognized by the NFA. So that's why we can write LM equal to LN. So given a non-deterministic automata, we can construct a deterministic automata that can perform the same computation or equivalent computation in order to recognize the language that is accepted by the NFA. And note that NFA have the non-deterministic moves, right? It need not be always that it must have non-deterministic move or epsilon moves, but those moves may not exist in a finite automata. So that means DFA can be think of as a particular type of NFA. So DFA is also an NFA, right? So so that means for a given DFA, we can find an NFA that recognizes it. So that this part is obvious actually. Okay. So this part is obvious that given a DFA, we can find an NFA that recognizes the same language as the DFA. So today we'll show that given an NFA, how to construct the DFA so that uh, we can recognize, we can accept the same language at the NFA. Okay, after this I'll give you an example, particular example, that how to construct that DFA for a given NFA. That is very important part. And then we talk about that. In fact, this is our today's plan. Okay, so this one we have already have discussed, and now we one part is left out, the equivalence, that we'll do today. So I think I have some other notes. I can use that one. The construct. Okay. So maybe I can just write it down. It will be even good. So I'll just add one more page over here. So we want to prove that equivalence of BFA and NFA. Okay. So basically, it's basically a theorem. Given a, I think it is not here. I have not included here. Uh, Given an NFA, say call it N, there exists a DFA, say call it M, such that language recognized by L is same as language recognized by M. Okay. So what is given here, that, so suppose your N is a DF, is a finite non-deterministic finite automata. So you have, so let, so this is your delta, then your start state, so, and you have your set of all final state. Okay, so maybe you can just q0 over here, n NFA. Okay, to construct a DFA M, so I call it q prime sigma delta prime q0 prime q0 prime and f prime. Okay, such that lm equal to ln. Okay, so how to construct that? We want to construct it, means you have to specifically tell what is q prime, what is sigma. Sigma is same as the given sigma. What is delta, the state transition, what are the states are there, what is the starting state, what is the state of all final states, all you have to define. Then only you can say, okay, I found this non-deterministic automata. And then you have to prove that the M recognizes all the string, those are recognized by the given non-deterministic automata N. Okay, so in order to do that, so first step is basically, step one is you define what is q prime, set of states, right? So this is nothing but, we straight I take the power set of q. So this is the set of all subsets of q. So for example, if you have q equal to 1 and 2 states, so then q is, power set of q is basically empty set, all subset containing just single element. Okay, so note that this is the q basically. Okay, so if there are n elements in q prime, there will be 2 to the power n elements. Okay, so it will increase the number of states to accommodate all possible moves that is done by the NFA. You want to simulate those moves, those computation using the finite automata, by deterministic finite automata. So then we want to define, so this is the set of states of M. So set of states of M. So this is q prime. What is the start state? Start state, that is, I call it q prime. So this we take the epsilon closure of start state of the q. So basically you can even write a set notation. So epsilon closure, if you remember that in the last class I just opened it, I Yeah, epsilon closure is basically, suppose you have this automata, non-deterministic automata. Epsilon moves are basically on receiving an non-empty receiving an empty symbol. The automata can move from one state to another state. For example, from state 1 to state 2, the automata can move on with an input epsilon. Epsilon means empty string. So the epsilon close, if this is a epsilon moves, and what is the epsilon closure? Epsilon closure is the set of all state which can be reached from that particular states. Say in this case you have 1, so from 1 to 2 it can go by epsilon moves, or you can stay here. So basically epsilon closure of 1 is the state itself, and if there is an epsilon moves, that moves take you to some other states. So epsilon moves can go to here, and note that there is another epsilon move from 2 to 3, so it will go, 3 will also come over here. I think here for 1, for epsilon 1, I think the 3 will be here also. Okay, so for any state q, epsilon closure is the set of all states which can be reached from q by using 0 or more number of epsilon moves. Either no epsilon moves or there is a number of epsilon moves. So in this case, the automata can move from state 1 to state 2 after 1 epsilon moves. Since there is another epsilon moves from 2 to 3, so it can go to 3 also. So epsilon closure is here in this case of epsilon closure of 1 is 1 1 1 1 2 3. So if we remove this one, if we remove the transition from 2 to 3 on epsilon input, then 3 won't be there in the epsilon closure of 1. Okay. So suppose at the very beginning, suppose I don't take epsilon closure, we just take very simple one, that we just simply assume that it is q0, that's the set q0. I will come to the case when epsilon moves are there, so we'll do that. Okay, so this is the start state. What is the final state? Final states is basically set of state such that I take an element of q dash, some subset, such that r intersection f is non-empty. That means this is the set of all subsets of q that contains at least one final state of n. Okay, so for example, if in this example you see that there is a final state 2, so 2, so final state I will be considering containing only 2, containing 1 2, containing 1 2 3 all. Okay, and containing 2 3, all subset that contains the one of the final state. So these 4 set will be in the final list of sets in the deterministic finite automata that we are going to construct. So now, as you assume that now we want to find the, to define, so here to now define delta prime, the transition function is very important that we want to design. So before going to do that, I just first take the case 1 such that n does not have any epsilon moves. Okay, n does not have any epsilon moves. Okay, so now I define delta prime. So delta prime, as you know, is a function, it's a deterministic finite automata. So it will be from sigma q prime cross sigma to q prime, right? So here I define delta prime as, so let R be a states in Q, and I want to uh, find out what will be the next states. Say A belongs to sigma one symbol, and I want to determine what will be the transition of this. So it's basically R is an element of Q prime, that is a state, basically state of the deterministic finite automata. I want to find out what are the states that the automata can move on. It will be going to one of the state in the Q prime, right? So in fact that denote actually one of the subset of Q. So this is, we write as like this. Say now again somebody came. Okay, so I define delta as the set of all Q belonging to Q. I am defining a subset basically, right? Such that Q belongs to delta RA. Okay, for some R belongs to R. So small r means this R is belonging to one of the state actually of the non-deterministic finite automata. So if I write some pictorially, I represent it. Suppose this is your R. It is a set of states in Q. So like this. So suppose this, after transition using delta on receiving symbol A, it is going to a set again because it is a non-deterministic finite automata. So this is your delta RA. Delta is a function defined for non-deterministic finite automata. I'm going very slow here because it's a construction that you have to understand. There are a lot of manipulation of the states of the set theory. Okay. So now you come over here again. So basically this is delta 1. So this is delta R2A. So on receiving symbol A, delta is taking that state to a set of state. So there will be multiple state over here. So there is one over here, one over here, and so on. So basically now you take their union. So there would be some more over here, right? So take all the union of this. Take their union, okay? So this union, this is your delta. This is your union delta R A, where R belongs to this. Okay. So this we called delta prime RA. It is very well defined because delta RA is well defined for every small r belong to capital R, right? So that's why I can straight write it here, uh, that this is nothing but union R belongs to capital R, small r A. Okay. So now it is done. Again somebody came, I have to go and accept it. Why so late? So claim is that so we have constructed already, complete construction is complete. I have defined each and every component of the finite automata. I have defined what should be the set of state, what should be the alphabet, what should be the transition function, what is a starting state, what is the final state. Okay, all are actually we have defined. So this is our f prime. Okay, so now we want to prove that so L M equal to Ln. Okay. Again, somebody came. I have to. That's why I don't like this. Anyway, so how to prove that? So I will give you proof hint. You have to complete it. So this means that X belongs to Lm if and only if X belongs to Ln. Okay. So suppose for first I one part I will show you basically let X belongs to Lm. That means delta prime Q0 prime X belongs to F dash. What is this one? F dash is set of all states that contain one of the each of the element contain at least one of the final state of the original automata, right? So this is your F. This is your F. So that means delta prime Q0 1x, this contains, this is basically set, right? So this is basically a subset of Q. And not only that, this subset, so delta prime Q0 prime x intersection F not equal to phi. Okay. So that means there exists a path. So I put another word here. So that means there exists a path from Q0 to one of the states in F prime on receiving string x as input to n, right? So that means n also accept x. So that means x belongs to ln, right? I just wrote it down. What is the meaning of this? So because this delta prime, so delta prime is basically, I will just explicitly write it down. So this is because q prime is just a singleton set, so this is nothing but your q0x, right? So that means has a this has an intersection with f, which is non-empty. So that actually has a, right, if I take the intersection, that means there is a final state. So basically which contains a final state, right? So that's why L n accept the string x, because starting from q0 it actually reached to one of the final state of the finite machine n. So since x is arbitrary, we can say every element of m is also is in ln. Okay. So this is one part that I have done the proof for you, right? So you do the rest. So suppose we call it say equation 1, for example. Similarly, prove that ln is a subset of lm. Okay. So this is equation 2. So I leave this as an exercise. Prove it, homework. So this one you have to prove it. By 1 and 2, lm equal to ln. Okay. Done. So one part is done. So case 2 will take, suppose n contains epsilon moves. Okay. So in this case, we modify slightly two things. One is the start state, another is the transition function. So define, basically redefine the start state as epsilon closure of this. Okay. So epsilon closure of this state. So this is in other word, we use another notation basically, that's called E of basically delta, sorry, Q0, E of Q0, right? So this is the notation we have used in the previous class. So if we take that one, so basically its meaning is that the set of all states of n that are reachable from 0 by 0 or more epsilon moves. Okay. So this is the ultimate definition of the start state. So based on the NFA, you can have Q0 prime different set. And now we also define our delta, say RA. So here, what we will do that, we take union of E of delta RA, R belongs to R. So this E is basically stands for epsilon closure. I'll explain it. What is the meaning of this? Okay. So here, basically what you have is, as before, in fact, slightly different. This is the set R. So R belongs to Q prime. That means R is a subset of Q, right? So there are element in R, many elements, R1, R2. They are basically states. And from there, it perform. So using delta moves, it can go to another set. So this is your delta RA as before. Similarly, from here, there is another set it can go to. So this is your R1A, this is your R2, this may be another R3 and so on. So there may be many other such transition. There may be many other transition. Now, from each of them, consider there are epsilon moves. So that may be another set. So that may be another set. Okay. That may be another set. There may be another set, and so on. So ultimately, you will have a set of state over here. So all are some state. So this is we take their union. So delta R A, where R belongs to capital R. Okay, where R belongs to capital R. So first you perform all the moves by using the definition that is given in the NFA. And after reaching to those states, you look at if we can reach to another state by epsilon moves. So this is nothing but the epsilon closure. Then we basically take the epsilon closure of that. Okay. So what we do that? So basically we take the epsilon closure E of this and take their union. Okay. R belongs to R. So in other words, basically epsilon delta RA is basically epsilon closure of delta RA. So this is a set. Always remember this is a subset of Q. Delta RA is a subset of Q. So that means delta RA belongs to Q prime. All are sets, state basically. In one machine, that is a set of states. In another machine, that is a single state. So basically, the single state in a DFA is simulating multiple state in the original NFA. Okay. So this definition is clear. If it is not clear, let me know. I will explain it. In fact, at the end, I will give you the example, concrete example for that. How many have joined today? 50. Okay, fine. Okay, so then next is the claim. This is the thing that we want to prove, that Lm equal to Ln. So that is basically x belongs to Lm if and only if x belongs to Ln. Okay. So I leave this to you. You have to prove it. Claim is, if claim is not proved, then it is not complete. Proof is as an exercise. Okay. So you complete it. If not, we'll see in the next class. Okay. Is it clear that construction is clear? How we actually construct it? So if not, let look at these things once again for a particular example. Uh, for this example, we construct the DFA. Okay. So illustration. Let n q sigma delta qf be an NFA. Okay. Where your q is basically has 3 states. Sigma is just 2 symbol. F is consist of only 1 elements, 1 state, and your q is the state 1, and the transition diagram delta is given here. Okay. So on state 1, 2, 3, somebody waiting in the lobby. Okay. I admitted. So now from state 1, what is the transition from the state 1? So basically it go to the state 3. I'll give you, so this 3, and on receiving symbol B it go to nowhere, so it's a empty symbol. So there is no transition from state 1 to any other state when the input symbol is B. If there is epsilon is input, that means empty symbol, then it go to the state 2. Okay. And when it is at state 2, On receiving symbol A, it can go to state 1. On receiving symbol B, it goes nowhere, and for empty symbol also nowhere. For receive from the state 3, on receiving symbol A, it goes to state 1. No, sorry, state 2, and on receiving B, it's go to 3, 1, 3 and 2, and on receiving empty symbol, it go nowhere. So if I just draw the automata, so that means this implies that state transition diagram can be written here. So here given that this is the start state. Okay, you see that q is basically 1 over here. So let me just draw it. Q1 is basically 1. Just forget about q, just 1, right? Just 1. Then okay, sorry, 2. So this is a final state. You see that it is given, and on receiving epsilon it can move to here, and on receiving A it can go to state 3. So let me draw the state 3 also. Okay, so from state 2, on receiving A it can go to state 1. From state 3 it can go to state 2 on receiving symbol A, and on receiving symbol B also it go to state 2, or it remain in the same state. Okay, so this is our given NFA. So this is basically our NFA. Okay, so this is our NFA. So note that there are 3 states. So we want to construct DFA M Q prime sigma delta prime Q prime F prime. Okay, so if we can determine it, then it's done. So first step, straight away. So step 1 is you define the set of all states. So this is just write it here. So empty set is a set subset that contains single element, subset that contain 2 element, subset that contain 3 element, so note that this is Q, and here empty symbol, this one actually we use this one, the state that corresponds to actually for no transition in N basically. Okay, so this phi is the state that corresponds to, see over here there is all or phi. So we actually perform a transition to a particular state designated phi. You can write in any way, actually you can give any level. Instead of this you can give it to any level, that is fine. But if we put in this way, then it is easier for us to prove things. Okay, now what is the start state? Step 2. So you want to find out this. So epsilon closure of Q, epsilon closure of 1. So what is the epsilon closure of 1? Say at 1 means it is included is 1. What are the state that I can move to by 0 epsilon moves or more epsilon moves? If I don't make any moves from state 1, so state 1 will be remaining there. If I make epsilon move, I can go to state 2. So that's why this is nothing but, so this is our start state. Okay, fine. So what is the final state? Set of all final state? Set of all subsets of Q. I am writing again here such again containing at least one final states of n. So what are those states? Sing 2 is the final state, right? So set 2 will be there. Any set that contain 2 will be there. Any set that contain 2 will be there. Any set that contain 2 will be there. Okay, these are the four states are final state. Now, as we have defined what should be the, so again I just recall it. I want to com compute it. Say on receiving a symbol, say maybe I put it x here. So x belonging to sigma, right? Sigma union, not union, sigma, just sigma. Sigma is basically our AB, right? In this case. So this is nothing but union of epsilon closure of, I just write directly epsilon closure of R. Okay, sorry, delta R x, or simply R x this. So x belonging to R. Again problem. R belonging to R. So here I shall use this one to basically determine all the transition, right? So if I write the automata again, it's better to always have side by so that every time I can look into it. So basically it is like this, just maybe just a quick draw. And B. So this is our automata. So now we want to find out for every state. For every state we want to find out. So one state is phi, and input symbol is suppose A. So phi is such that it cannot go to any other state, right? So it remains same. In fact, in fact, delta phi b for any symbol it remains same actually. Okay, it cannot move out to anywhere. So for state 1, what will be the transition state after receiving symbol A? So basically this is the epsilon closure of 1, right? If I write little bit clearer, delta 1A. Okay, so that means the you are at here. Okay, in this case place. So either you stay you go to on receiving A, go to 3. So delta 3. So this is epsilon closure of delta 1A, means after receiving A you go to 3, right? So it will be 3. So what is the epsilon closure of 3? Because there is no epsilon moves from 3, it just remains the same thing. Similarly, you compute delta prime 1 B. At 1, it cannot move out to anywhere from it. So basically this is epsilon closure of delta 1b. So that means epsilon closure of 1 to b is a phi basically, right? It's a phi. So it cannot go out because at 1, if it receive input b, it cannot go anywhere. So in the table itself, you see here on receiving b, it is phi. These are phi movement are there. So it halts basically. It cannot perform any other computation. So then we have done for 1. Basically, we have done for say input A and B. I am in state phi, so it will be phi, it will be phi. I am in state 1, it will be 3, it will be phi. I am state 2, what will be here and here. So you compute. I am showing this. Next time I will not show everything, you have to do it yourself. So from 2 on receiving A, it can go to 2 here on receiving A, right? So that's why epsilon closure of, so basically delta 2A, so epsilon closure of from 2, right? Okay, sorry. From 2 on receiving A is go to 1. Okay, I write 1 here. And what is the epsilon closure of 1? This is 1 and 2. Okay. So I write 1, 2. What will be delta prime to B? What will be that? Okay. So this is again epsilon closure of, I am showing the steps again. So 2B, if it is at receive B, it can go to state 2 or it can stay in the same state 3. So that means this is the set 3 and 2. Okay. So this is same as you basically take the union epsilon closure of 3 and 2, right? Maybe I can give you epsilon in a different way. Say epsilon closure of 3 union epsilon closure of 2. Okay. So epsilon closure of 3 is 3. Epsilon closure of 2 is 2. So they remain in the same. So one second. Uh, delta to B, it can go to state 2 or it can go to state, it can remain in the same state, right? But going to state 2, it will be there. Fine. Okay. So that means there may be some discrepancy with my notes. There is some mistakes there. So this one is all right. So you put it like this. So 3, 2. Okay. 1, 2, 2, 3, 2. Okay. 3, 2. Fine. So this is the way actually you can evaluate one by one, and you fill up the table. You fill up for all possible state. You will see a state transition diagram there, and using the state transition diagram you can draw the, using state transition table you can draw the diagram. So basically once you have completed the list over here for all state and for all inputs, you have to know actually what is the transition going on. So after you have done it, you can draw the final diagram. So maybe I can just show it here. I already have it. So basically, uh, yes. So you give all the states over here. So this is the 5 state. Another is 1. Another is 2, 3, 1, 3, 1, 2, 2, 3. All 8 states are there. You count them: 1, 2, 3, 4, 5, 6, 7, 8. All states are there. So I can just draw the original one here just to compare. Oh, just a minute. I have a phone call. I just side by side. I just draw it here. So just to compare actually. Uh, so 1, 2, 3. So epsilon moves. So here, start state, as we have find out that it is 1 2. From 1 to 2 on receiving A, in fact it has to move to from 1 to 3. So that's why there is a movement from here, from this state to here. Okay. So in fact you can look into the table, in fact. So using that computation that we have done over here, so that actually give you what should be the uh, edges between the states. So on receiving A, from start state it go to 1 2 3 state. Another, on receiving B, it go to 5, because in this on the right, in the NFA. So this is your DFA. There is no transition on receiving symbol B at the state 1. So that's why it's going to state B. Similarly, at state 2, there is no transition for input B. So that's why there is a you know state transition to the state 5. Similarly, uh, from 1 and from 2 also is happened here. And note that there is a observation here, that first of all, this is a DFA, right? All are deterministic transition. There is no non-deterministic transition. And here you'll see that for this state 1 or for this state 1, are they reachable? Are they reachable from the start state? Can you reach here 1, or reach 3, or reach 1 3, or here? Can you reach here? First of all, there is no incoming edge to the state 1, so you cannot reach here in the state 1. Okay, so that's why we can remove it. That means there is no input string that could take the finite automata to this particular state. So its computation will happen in the other state. Nothing will happen here. So this is redundant. We can remove it. Similarly, there is no incoming state from starting state to the no path from starting state to the state 3, because there is incoming path from 1 to state 1 to 3, but there is no path from starting state to state 1. So that means this particular state is also not reachable. Similarly, from 3 to 2, there is also a edge going, but there is no other edge coming. So State 2 is also not reachable, and also 1 3 is not reachable. So this four state that I just make a box around them, or maybe I can highlight here. uh, See, state, so this one, this one, this one. So these states cannot be reached from the starting state, so we can remove them, and we we can give the finite automata that simulate the non-deterministic machine and accept the same language. After reduction, actually what we get again is basically four state machine, and that is given by here. So this is our final answer, that this is the machine, this is our DFA. Okay, DFA M such that L of M equal to L of N. Okay. So is it clear? Is it clear that how you follow, how you construct the DFA? So it's a, explanation is long, but thing is that when you compute it, only one part is, you have to do it very carefully. The part here, for all state, you have to compute the state transition. Otherwise, you cannot draw the arc here, directed arc. Okay. So, now we have done the proof also. We have come up with one example, that using that example, actually we learn how to construct the DFA that actually equivalent to an NFA. So next time, if I give you uh, some other problem, some other NFA, you have to construct the DFA. I will give one assignment problem. Okay. So there will be one such problem will be there. There will be problem for construction of DFA for, you know uh, for giving a language set, you have to construct a DFA that recognize it. So those things we have done, and also you have to do it in the assignment also. And once the assignments are submitted, I'll discuss the solution in some tutorial class. Okay. So next one is the closure property. uh, so I also have the notes, so I can use that note as well. So closure properties of regular language. I think today also, just let me see. Fine. Yes. So next one that we want to do, that closure properties of one second. Yes. So basically, we do something here, that regular language closure property, basically closure property. So you have an alphabet. Sigma is the set of all string over alpha, over sigma, and L is basically a, not a, this is the set of all regular languages over sigma. So this is precisely, if I write down, so this is basically subset of sigma such that there exists a finite automata such that fa automata say M. So if I write mathematically precisely, so this is the set of all regular languages, then L is closed under regular operator. What is that? Union, concatenation, clean star, or just we say star operation. Okay, so these three union one we have already done it by DFA, but we use another construct that is easier using non-deterministic finite automata. We shall prove it. Okay, so so far if you have any doubt, please tell me. I will discuss it again, otherwise I'll just straight I try to prove these theorems, that's all. Okay, so if you don't understand any part of the previous things, let me know. So here the first theorem that we want to prove, that let L be the set of all regular language over an alphabet sigma, then for any language A and B in L, that means AB are regular language, then A union B is also in L, that means AB is also regular. So this is the outline of the proof. I will give a constructive proof basically. So A, B belongs to L, that means there exists say DFA or NFA such that, say I can call their name maybe DFAs M1, M2, such that L of M1 equal to A and L of MT equal to B. So let your M1 is Q1 sigma delta 1 Q1 F1. Okay, Q2 is delta 2 Q2 sigma delta 2, the final start state Q2 and final state of state is F2. Okay, so to construct an NFA M such that L of M equal to L of M1 union L of M2. Okay, so we want to find out some finite automata such that it is Q, same alphabet, some delta function that we will define, some start state Q will define, and some state of all final state will define. Okay, so how to define that? So here is a very simple construct. If you remember our previous proof, that was lengthy and more detailed structure was given, but here it's even more simpler, because we already know we are given Q1, given Q2, delta 2, all are given. So based on their definition, we can actually define an NFA very easily. So suppose I draw the two NFA, two DFA as this. Suppose I have say M1 and M2, some black box. They are computational machine, some black box that I want to simulate. So this is our machine M1. Okay, it has some start as final state, maybe some other final states are there. Similarly for machine 2, there is a start state Q2. Okay, and some other states, so maybe there are from final states as well. Okay, So now I want to, so this is your M2. I want to determine one machine that simulate both. Okay, one non-deterministic automata simulate both. It's just like your computer CPU. There are multiple core. Every core can execute different program, give different output. Okay, so they are running in parallel. So here the NFA we are constructing here is similar to that. We are simulating M1, M2 in my new machine so that the new machine can recognize whatever M1 or M2 can recognize by simulating them. Okay. So in order to do that, what I will just make some modification. So that modification is basically I will add one state over here that I will make a final state, and I will make a epsilon move. Okay, I'll make another epsilon move over here. So basically by taking epsilon moves, the execution path can go from starting state q0 to q1 or q2 simultaneously. There are two execution paths. So if that input string belonging to M1, then it will be executed over M1 and reach to some of the final state. If that input string, suppose you have the input string X, if that belongs to LM1, so that means after epsilon move, the start execution from here, and then by following some one, it will go to some of the final state over here, right? So so that X will be accepted here. So whatever final state in M1 and M2 are there, I put those in my new machine also. Okay, so this is my new machine. Okay, so this is my new machine M, and here Q0 is the start state. It's a new state. Okay, and then my Q will be set of all state is basically Q1, Q1, so Q1 union Q2 union Q0. Okay, what will be the final state? This is just F1 union F2. Okay, so sigma is same, sigma is same. Okay, now I want to define delta. What should be my delta? So this is very important part. So delta RA, that I want to define. Okay, so first of all, it is phi if R equal to Q0 at start state and A not equal to epsilon. So we force the machine to move Q1 or Q2. It cannot go to anywhere else. So that's why we force the transition such that on if the input symbol is something else, it will go to the some, it will not move anywhere actually, right? So that means now next one we define if it is epsilon. So if it is epsilon, it will be my q1 and q2 if r equal to q0 and a equal to epsilon. This corresponds to this epsilon moves. So this one, epsilon moves. Okay, so this particular part, it is equal to ra if r belonging to Q1. Okay, it will be delta 2 RA if R belonging to Q. That means after epsilon moves, once the computation enter into this part, into this block that corresponds to machine M1, all the state transition happen according to the delta 1, the transition of that M1. So it will simulating basically. Similarly, when it enters into the machine M2 states Q2, all the transition after that will happen there according to delta 2. Okay, so next claim is that L of M equal to L of A union L of B. Sorry, not LALB. Uh, M1 union L M2. So that means X belongs to LM if and only if X belongs to LM1 or X belongs to LM2. Okay. So I'll give you only one part, proof of one part. Suppose let X belongs to LM. Okay. So that means delta of Rx, delta of Rx belongs to the final state, right? So this is equal to F1 union F2, right? So this implies that either delta Rx belongs to F1 or delta Rx belongs to F2. So first of all, you can assume that say X is basically in fact you don't have to assume anything here. Okay? So I think we have to consider this not R here, it should be yes. So it should be Q0 start state, right? So that means if X not equal to empty, right, empty string, so then it's basically Q1 X or Q2 X. So that means either X belongs to LM1 or X belongs to LM2. Okay. So since X is any string, right, in LM, so this implies that, so this one I have proved for you. So second part you should prove for yourself. Okay. So this is part one is proved for you. So next prove that. So similarly, my handwriting is not so good. I'm sorry. Similarly, proof LM2 is a subset of LM. Okay. So call this second equation. So equation 1 and equation 2 gives so this will prove So this one I leave you as exercise. So take this as exercise. Okay. Is it clear? Is that clear? I want to know, I want to hear whether you understand or you don't understand. So if you don't understand, please let me know. I'll explain it. Otherwise, I'll move on. I have few more minutes, so I think I can do the rest of the thing. So here, basically, under closure operation, under concatenation. So basically, closure under concatenation. I don't understand why you don't respond. All are muted. Yes, no, something I want to hear, whether you're not sleeping at least. Uh, Fine. So here is the idea that A is belonging to L, B is also belonging to L, and they are regular language. That means A is a regular language, B is also a regular language. So as before, you will have there exist DFA, say M1, say Q1, sigma delta 1 Q1 F1, and DFA M2 Q2 sigma delta 2 Q, sorry, F2, such that such that so this is there exist, there is a difference, I will tell you. So maybe I, it's not same. So this is means there exist is the reflected E, and this one is reflected belongs to, right? It means there exist, such that. So this means such that. In other word, I can just write such that. That is also fine. Such that such that M1 equal to A, L, M2 equal to B. Okay. So what you have to do that to construct NFA, N equal to Q. Same thing, I am not writing all. So this one such that L of N equal to AB. Okay. So concatenation. So if you want to put a small circle there, that is also fine. So how to do that? So let me give you the figure, the diagram. It will be easier to understand. So basically, concatenation means you're adding one after another. So suppose A is there. So this is your A, is basically nothing but LM1, and also there is B. So here B, so LM2, okay, and it has a start state, okay, say Q1. It has a start state Q2. It has some final state. Let me little nicer. Okay, so it has also some final state. Okay, so some other state may be there. So even I can draw in a different color. That is also fine. So there are other states are there. Okay, so now as if you are just putting one after another. So one string is coming from A and another string is coming from B. So we are concatenating. So A is from A and B is from B. So AB belongs to AB, right? So this is the thing that we will be doing here. So we concatenate this machine actually to make a new machine, that simulate both. Okay, so maybe I can uh, so this is the, I will make its start state, and for every final state of a m1 I make epsilon move to the starting state of m2. So I'll do that. So if there is other final state over here, so if I have more final state over here, I can also do the same thing. So what I'll do here, I'll also put some epsilon moves from here. So that means that new machine that I'll construct over here, so okay, so this is my new machine. Note that what I want to do, I want to take a string x in A. So after taking, say, starting from q1, if it receives A, then it will reach here. So another is y belongs to B, right? Y belongs to B, and my input string is x of this form, x and y. So on receiving x up to x, suppose it possesses x1, x2, xn, y1, y2, ym. So it start from here and then it go here. As soon as go to xn, so this is my xy, right? So this part is basically x, this part is y, this is x. So on receiving x part, it will be at some of the final state of the machine m1, and then after epsilon moves, that means machine can move to q2, and then it will get the symbol from y, that means y1, y2, ym. So then the machine will transit the state from q2 to any of this final state of the m2. So finally, after receiving xy, after receiving xy, it reach here, one of the final state over here, right? So that means this will be accepted. So note that here, when we do the concatenation, so if if A contain epsilon, note that one thing, if epsilon belongs to A, then B is a subset of AB basically, right? If epsilon belongs to A, epsilon belongs to B, then A is a subset of AB. Okay. So that means here, when it receives some string from only from A, suppose it receives some string only from A, then it will be here only in the final state of m1. So that is also accepted. Okay. Otherwise, it can move to a epsilon. So suppose epsilon is it's not there in B. If epsilon is not there in B, means there will be something. So any string from AB will be of this form. So where x not equal to epsilon, y not equal to epsilon. So in this case, always the machine will end up with some of the state over here. Okay. So basically, this is our final this is our new machine, non-deterministic automata, that we keep all the final state as it is. We actually just add some epsilon moves. That's all. So Q is Q1 union Q2. Q0 is Q1. Okay. And say F is basically our F1 union F2. If epsilon belongs to B, right, we have to keep F1. Otherwise, if we assume that epsilon doesn't belongs to either A or B, so all elements of A and B are non-empty string. So in that case, we consider this. So we assume here, we can assume that let epsilon does not belongs to A, epsilon does not belongs to B. Okay. So then we include F1 union F2, and it is done. And delta, we then define delta. What is happening? We define delta as RA equal to, say, delta RA if R belongs to Q1 minus F1. We don't want to make that R is belonging to the final state over here. So there may be some state transition. There may be some state transition from the final state of M1 to other part of the machine. So we want to prevent that. Okay, we want to prevent that. So we make sure that the next part will be recognized from the string that is coming from the second set B. So if delta 1 RA, if R belongs to F1 and A not equal to epsilon. So that means there may be some epsilon moves from here, right? So if we take NFA, M1 and M2 are NFA, then there may be epsilon moves from the final state of the machine M1. So we want to prevent that. We want to make sure that epsilon moves only be possible from the final state of M1 to the initial state of the M1. Okay. Now, what will happen if A equal to epsilon? So then we'll keep R1 R A union Q2. So if R belongs to F1 and A equal to epsilon, so we are allowing epsilon moves. So this inclusion of this Q2 actually tells about the epsilon move. Okay. So next, if it inside that second machine state, that means if R belongs to Q2, in that case we simulate by delta 2. So note that here first R belongs to Q1, so we simulate by delta 1. R belongs to Q1 also is simulated by delta 2, but epsilon is not equal to A not equal to epsilon. So input symbol is non-empty. And now delta 2, we take delta 2 when it is in the Q2. For the set of all state, the movement transitions we are copying from M2, we are simulating. So this basically, this is the for simulation of M2. So here for simulation of M1, okay, in a sequentially. So sequentially, X and Y are coming from A and B. Similarly, we simulate the machine M1 and M2 accordingly so that it can recognize the suffix by M1 and prefix by M1 and suffix by M2. Okay. So next claim is that LM is same as LM1, LM2. Okay. I give you this as an exercise homework. So it will be as before. I have shown you two cases actually. So HW exercise. Do it at home. Any question so far? So I think the next one we'll do in the next class. So next class. Today is 70921. Okay. Or I can leave you as an exercise. No. This one I give you the construction. Then you can do it yourself. Okay. Any question? Let me just take some screenshot. Can any of you take the responsibility to get the attendance and send to me? CR, can you do that for today? Hello, can you hear me? Hello.
Yes, sir. Yes, sir.
Using this now, I'm not using slides and all. So, is there anything that I can improve upon so that it will be easier for you? So, is it okay when I use this writing online? I am actually using a pad for that, writing pad. So, is that fine with you, or anything that I can improve upon? I am not sure. So, it's like writing on a board as usual in the classroom. So, I think it will save a lot of time for me, and also I can write one by one line and you can follow it. If I just put it everything on a page, so you will just look around and read everything. So I think uh, this kind of way of teaching maybe give you more attention, that you can concentrate on certain things that I am currently on. Say I'm writing on some line or some argument, so you can follow it better maybe. Okay, you are so introvert. Probably you are not
Sir, we
speaking
have
at all.
responded.
That works.
Yes, sir, we have responded. It's so fine.
Okay, it's fine. Okay,
Yes,
so we continue, and thank you all. So today class is over. You can leave now.